Welcome to Finite Element Analysis lectures by Civil Thinking, and this is our next class on Finite Element Method series. Now, before I move on, I suggest you to please watch the video lectures on Finite Element Method one by one in sequence as in the playlist so that you understand better. The playlist link is in the description, or also you can click on the pop-up on your screen. Now, coming to the today's class. Now, in this class, we will see what are the different kind of analysis in finite element method, or in computer aided engineering. Okay, because after all, finite element method, it is used in the computer softwares. Okay, so in general we can say all of these analysis are kind of types of analysis in computer aided engineering, or right, or CAE. Okay, so the first one is linear static analysis, then second is non-linear, then third is dynamic, then we have buckling, we have thermal, we have fatigue, we have computational fluid dynamic analysis, we have crash analysis, and then we have NVH analysis. Okay, so these are the basic types of analysis. There are obviously more than this, but they are the basic ones. Okay, so let's begin one by one. Now let us first see linear static analysis. Okay, now this linear static analysis, it is made of two words, right? So it is linear plus static. Okay, so what is it? Now what is a linear? Linear means a straight line, right? So when we have like this, for example, this is a straight line. Okay, straight or linear line. Okay, for example, this is y, this is x. All right, then we can represent this equation in terms of the equation y equal to mx, right? We can represent this straight line with the help of an equation y equal to mx. What is m? M is the slope, right? Slope. Okay, so when you see such kind of analysis where a straight line or a linear line is involved, we call it as linear analysis. Okay, now in case of finite element method, what we exactly mean? We mean when there is a linear relation between stress and strain, or force and displacement. Okay, when we have a linear relationship between these two, the way we have a linear relation between x and y, right? In this equation, x and y, there is a linear relation, right? So if I replace this with strain, and I replace this with stress, then according to Hooke's law, stress is constant E times strain, right? Now what is E? Because m is the slope, so in place of m we have E, so E is the slope here, right? Now we have E, right, which is Young's modulus. It is the slope. Okay, so in a straight line, what is the slope on different points? The slope on different points is what? Constant. Okay, so because it is a straight line, it is a linear line, so this is the reason we say in linear analysis E is constant. Okay, E is constant because E is the slope, right? Now E is constant. Now we have, if we multiply E with I is the moment of inertia, it becomes what? K, which is stiffness, right? So assuming we have a uniform body, okay, the cross section is uniform, then EI is stiffness, so it also becomes constant. Okay, so in case of a linear analysis, we have what? We have a constant stiffness. Okay, now in finite element method, because we always divide a body, as we have understood in the previous class, we divide it into number of elements, right? So here will be K might be different here, and we have K here, we have K here. So this is the reason we don't talk about single K in finite element method. Rather, we talk about a series of K's, series of stiffnesses. Okay, now if they are constant, that is another thing, but the thing is that we have different stiffnesses of different elements, right? And we put them in the matrix. Okay, so this is the reason we talk about stiffness matrix. Okay, because there might be questions on your mind, because if it is K, because this is not a single body right now, right? This is not single body, right? This is multiple elements, right? Multiple elements. When it was not discretized, then it was single, we would have talked about K, but since we have divided it into multiple number of sub elements, right, discrete elements, so we have multiple number of K's, and we arrange them together in a matrix, right? So we have a constant matrix, this stiffness matrix, right? So this is the concept of linear analysis. And then we talk about static. Okay, now what is this static? Static means what? Now static means either at rest or moving with uniform velocity. Okay, when there is no acceleration. Okay, so if a body is at rest, okay, it is truly at rest with respect to a frame of reference, or it is moving with a uniform velocity v, then we call this is a static body. Okay, now in case of a static body, what do we have? We have equations of equilibrium, right? Summation of f of x, right, summation of f of y, summation of f of z equal to 0. Similarly, summation of movement about x or about y or about z is equal to 0. So these equations are applicable on a static body, right? And also the force acting on a body. Okay, the force is constant with respect to time. Okay, for example, if this is force, then the external force does not change with time. Okay, so in case when we have what, a constant force, okay, constant force, okay, then we have this static analysis. Okay, now when in a body, in an analysis, when we come with a situation where both the things exist, right, where both of these are together, okay, they exist, these two conditions exist in an analysis, then it is what? It is linear static analysis, right? So this is the concept of linear static analysis. Okay, so let me write here. So in linear static analysis, okay, we have a linear relation between stress, strain, okay, right, or force displacement, right, also stiffness matrix K is constant, okay, and force is also static, means force is not a function of time, okay, it is constant, because that is the condition of static. Okay, so when we have such kind of condition in an analysis, we call it as linear static analysis. Okay, now we can go further more deep in it, but I think it is enough as we are just introducing it. Okay, so let us come to another topic now. Problem with linear analysis. Now what is wrong with linear analysis? Now when you come to a real product, for example steel, okay, or any kind of material, what is the relation of force and displacement? What is the relation between stress and strain? Unfortunately, it is not linear. Okay, not linear. Okay, let me give you an example. For example, let us take some metallic body like steel or something. Now if this is strain and this is stress, now up to some point it is straight. Okay, it follows linear analysis up to certain point. Then what happens when you further increase the stress? It changes. Okay, something like this. Okay, now this is elastic limit. Okay, elastic limit, and remember, only up to elastic limit this is a straight line, right? Or in other words, we can say Hooke's law is valid only up to elastic limit. So when you have an analysis, okay, when you are analyzing a product, or a structure in FEM, and we have this the loads are only up to the elastic limit. Okay, so up to the elastic limit, it is fine. We can use what? Linear static analysis. Okay, we can use linear analysis. But when we increase the stress further more, okay, then this is not linear, right? As you can see, this is not a straight line. Okay, so this is not linear, right? Or we call it as plastic. Okay, now up to this point it is linear or elastic. Why elastic? What does it mean to be elastic? Because if you increase the stress, the strain will increase. If you increase the stress with 2 times, the strain will also increase 2 times. Okay, or 3 times. If you increase stress with 1 step, okay, the strain will increase proportionally, right? That is called as elastic body. And if you decrease, now for example it was 3 first, okay, it was 3, right? Then you decrease, you come back in this curve. For example, now you put the stress to be only 2 times, so this will also change 2 times. Okay, so it is a reversible process. Okay, reversible. And we have the strain is proportional to the stress. Okay, but in case of plastic analysis, when you go beyond this point, you see, if you were initially at here, then you try to decrease the stress. Okay, for example, here the stress was for like 4 times stress. Now you try to decrease the stress to like 2 times. So you wouldn't expect here it is 4 times strain and here it will be now 2 times strain. Okay, 2 times strain. No, because it is not proportional. Okay, this is not a straight line, because these things, this proportionality exists only on a straight line, right? So this is why we call it as plastic. Okay, because the restoration is not proportional. Anyways, I don't want to go in the complex wording so that you will not understand anything. I will keep the things very much simple. I will keep my wording very simple. The thing is that this is a straight line. The linear analysis exists up to this point, right? Simple. And when you go beyond, now this is not a straight line, this is not linear. Okay, so now what our actual topic is problem. We have to see the problem. The problem is, now the problem basic in FEM is, up to elastic limit we don't have any problem. Okay, no problem up to this. But what happens when you increase the stress beyond? The strain should be like like here or here, right? But if you keep the analysis like linear static, okay, for example, you keep the analysis linear in finite element method, you have assumed that this is a linear, and you increase the stress, you increase more than the elastic limit. Okay, then instead of going through this, instead of following this path, what it will follow? It will follow a straight path. Does it make sense? Why it follows straight path? Because the true stress strain curve is this, right? But it will not follow this path, it will follow this path. Why? Because what it knows, it only knows that we are in linear analysis, right? Because linear means straight, so it will not recognize this thing. Okay, then you will have problems. You will get so much stress. Now if you will carry out analysis of a beam or something, okay, now it will bend like this, okay. Up to this, if you further increase, it will fail, okay. There will be fracture, there will be a fracture or crack here. But if you set the analysis to be linear, okay, linear, it will not show any crack or anything. Why? Because it is following this straight curve, okay. And what it will show, instead of showing a crack, it will show too much stress, okay, high stress, high stress, Now let me tell you, when there is a high stress, okay, for example in ANSYS or ABAX or SolidWorks or whatever FEM software you are following, you will see, if you see the stress curve, stress graph, there are high stress regions, there are low stress regions, okay. Then high stress regions are shown with red color, okay, red color. So what happens when you do the same analysis in the laboratory, okay, you will see a real crack, right? You will see the body has failed. But in ANSYS or in any FEM analysis, since you have kept the analysis to be linear, there will be no crack, okay. Instead of crack, there will be a red color, okay, intense stress. And then you will have to know, if you know the property, if you know, like, okay, this body is, it fails, there is a fracture at this, for example, at some stress, for example 10 megapascal, it will fail, okay. Then you will have to analyze manually. This red region is basically not high stress, it is basically a fracture, okay. So you will have to use your mind then, okay. Now when you keep a non-linear analysis, it will truly follow this path, okay. Then this is the ultimate stress point and this is the fracture point, okay. So this is the problem with linear analysis. The problem is it does not recognize non-linear curve. Why? Because it is linear. Instead of showing stresses on this, it will follow a straight line beyond elastic limit. Up to elastic limit is fine, but beyond elastic limit, it will behave or it will misbehave, right? So this is the problem with linear analysis, okay. Now let's move on. Now non-linear analysis, okay. So basically this is non-linear analysis. After this we have linear, and after this the plastic region, this is non-linear analysis, okay. So now let us see when different scenarios of non-linear, okay. Now geometric, like when we have large deformations, what happens during large deformations? When there is a large deformation, okay, a beam, okay, there is a very high load on it, okay, it will deflect too much, okay. So what happens because of large deformations? The structure of the body changes, okay, the internal structure changes. So E also changes, okay. So because EI is stiffness K, so it also stiffness changes, right? So stiffness matrix K will also change. It means K is not constant, okay. So in case of large deformations, because the internal structure of the body changes, so then we have to set the analysis to non-linear analysis, okay. So in case of large deformations, when we have large deformations, keep in mind that is a non-linear analysis, okay, because like I have told you, stress is equal to E times strain, okay. This is Hooke's law, right? This is linear, right? But it is only valid for small deformations, okay. If you increase the deformation, this is not applicable. Okay, so now we have geometric non-analysis. So when we have large deformation, then we have material non-linear analysis. Now material, we have 3 points beyond elastic limit E, as I have told you earlier. Let me show it again. Now after this is elastic limit, right? This is elastic limit. Then after E, what happens? This is the actual curve, right? Stress strain curve. And as you can see, this is not linear. Is this straight line? No. So this is not linear. So this is what it is saying. Okay, so beyond elastic limit you will have non-linear analysis. Okay, and then we have within elastic limit for non-metals. What does it mean? You know, this was the curve of what? A metal, right? Like steel. Okay, metals. But what happens in case of non-metals? You know, when we have a non-metal, the curve doesn't follow this Hooke's law. Okay, the curve is like from the beginning. Okay, for example, this is the elastic limit. Even before the elastic limit, this is not straight line. Okay, this is not a straight line, this is curve. Okay, so even before the elastic limit, the analysis, the stress strain or force displacement curves, they are not linear in case of non-metals. Okay, so when we have non-metal analysis, okay, even within the elastic limit, keep in mind that is a non-linear analysis. Now there is creep. Now creep is what? Creep is basically when a body undergoes deformation in, you know, this is long time. Okay, when a body goes under deformation at constant load, and when you keep the load, okay, for example P constant, okay, and after so much time it will deflect even further. Okay, this is called as creep. And remember, because creep is a long time process, in the long time process, again the internal structure of the material changes, which leads to the change in E. Okay, which leads to the change in I. So the K is not constant. Okay, in case of creep. Okay, so since K is not constant or E is not constant, that is also non-linear. Why? Because the slope E is slope, right? So when a body doesn't have a constant E, constant slope, it automatically means it is not linear, right? And when we have a linear, E is always constant at every point. Okay, so now in non-linear, E is not constant, which causes the, you know, this line to be non-linear, right? So it is a non-linear analysis. Okay, then we have contact. Okay, now in case of contacts, what happens? Okay, let me erase this first. Okay, now in case of contacts, now there are two kinds of contacts. Okay, there is a gap, and there is contact. Okay, now gap is when we have some gap between two objects. Okay, this is gap, right? This is object 1, this is object 2, material 1, material 2, and there is a small gap between them. Okay, now this gap is also under non-linear analysis. Okay, why? Let me tell you why. Because, you know, let me try to illustrate it with the help of an example. Okay, for example, you have a beam. Okay, now here is, you know, a support, but we have a gap here, right? Gap, and here is a support, it is in contact. Okay, because we have gap and we have contact. Okay, this is contact, in contact, and there is a gap. Okay, now at, for example, P is a load. Now at P equal to 0, what happens? This will not deflect, right? So remember, there is a reaction. You know, when you apply a force on a body, it reacts back, right? There is a reaction. But since there is no contact, there is no reaction. Okay, now let us say you increase the P to now, for example, 20 kilonewton. Okay, because of this, now it will come close to this, right? Let us say it touches, right, because of 20. Now the moment it touches, the reaction begins, right? Initially this reaction was 0, right, because it was not in touch. Now when you increase the load, for example, reaction is now here 2 kilonewton. Okay, now when you increase the load after 20 to, for example, 40 kilonewton, okay, now this will compress it. Okay, due to the compression, the the body, the shape will change, there will be deformation. Okay, so when there is deformation, the E changes, the stiffness of the material changes. Okay, so the reaction will also change. Okay, so let me show it with the graph. Let us say this is reaction. Okay, let me call this as R1. Okay, R1. Initially, let us say this is what? This is P. Initially, at 0, what was the reaction? 0, right? Then what happened? When you increase the load, okay, you increase the load to 20. Now what happens? There is a sudden increase in reaction, right? Then you increase it to 40 kilonewton, and there is increase in the stress. Okay, and this is not linear. Okay, so this is our curve. Okay, if you don't understand anything, or if I'm not explaining well, you can ask in the comment any questions, whatever you have. Okay, you can contact me if you have any doubts. Now tell me, what is this? Is it straight? Now this is straight, this is linear, right? This is straight line, this is linear analysis. But what is this? This is, no, we have a step here, right? This is step. This is not linear, right? Because it is like this. So can you see now why it is non-linear? The gap analysis, the gap simulation is non-linear, because you can see the curve. Okay, now we know about the gap. Now let us talk about contact. Contact is when the body are touching each other. Okay, now initially when the P was 0, let us call this as R2. Okay, R2 was also 0, right, because there was no load, so there will be no reaction. Now when you increase the load to 20, what happens? The E will change. Okay, also in this case, because you are compressing at 20, it touches, right? When you increase it to 40, there will be deformation. The internal structure of the body will change, which will cause E to change. Okay, when there is change in E, it means it is not a straight line. Okay, now to be more accurate, it could be like something like this. Okay, why? Because if you keep it like this have a constant E, right? But due to the compression, what happens? E changes. Okay, so the more appropriate will be like this. Okay, so more appropriately it is like this. Okay, now let's come back. Now initially when the P was 0, reaction was 0. When you increase the P to 20, there will be some reaction will increase, for example 3 kilonewton. When you further increase the P to 40, it will compress. Okay, the compression will cause the internal deformations will cause what? E to change. Okay, when E will change, what is going to happen? The the reaction will change, but not proportional to 40. Okay, for example, at 20 we had 3, right? At 20 we had 3 deformation. Now if it was linear, 40 is double of 20, so it would have also been 6, right? So we would have expected what? If I draw the graph here, this is R2. Okay, let me show it here. I don't know what is happening. Okay, so if it was 20, if for example this was 3 corresponding to 20, if it was linear, because 40 is double of 20, so there should be ideally 6 if it was linear, right? But due to the compression, E will change. When E changes, the slope of the curve changes, okay? So it becomes non-linear, okay? So this won't be 6, okay? This will be like maybe 7, or maybe less than 6, okay? It could also be only 5, okay? That depends on the body, but the basic concept is the E will change, the relation won't be a linear relation anymore, okay? So if I draw it, this is the reaction 2. Initially it was 0. When you increase, it becomes to, for example, 20 like this. Then you change it 20 to 40. You should, if it was linear, it would have been like this, right? It would have been here, right? But it is not linear. Maybe it will change like this, or it will change like this, okay? So for example, let us say it changed like this, okay? So this is what? This is the reaction now at 40, okay? This is the reaction, okay? Here it was reaction at, no, here it was reaction at 20, okay? And here it is reaction at 40, and the basic concept is it is not linear, okay? So this is the reason I have written here the gap and the contact, they are both under what? They are both under non-linear analysis, okay? So I think we have talked about everything, okay? So in case of non-linear analysis, what do we have basically? Either what? Either we are in this range, okay, or it is a non-metal, okay, or it is a gap or a contact, okay, or if there is a large deformation, what happens? Because of large increase in the deformations, the internal, the stiffness changes, the E changes, okay? So we are not, this Hooke's law is not applicable anymore, and the analysis become non-linear, okay? So let's move on. Now we have dynamic analysis, okay? Now what is dynamic analysis, okay? Now dynamic analysis in the situation when, when applied force is not constant, okay? We call it as dynamic load. What's dynamic load? Initially I have told you in static analysis what happens if this is the force or load as a function of time, okay? It is a straight line, because it is not actually a function of time. The force remains constant every time, right? That is static. But in case of dynamic analysis, the force changes, okay? The force changes anyways, okay? It could be like this, okay, sinusoidal. It could be like something like this. It can be anything, whatever it is. But the thing is that the external force changes with time t. This is called as what? Here the f of t is called as what? Dynamic load, okay? And when a system, when a body, okay, a body or a system, it is subjected to what? A dynamic load, okay? This analysis, we keep it under what? Dynamic analysis, okay? Now there are more certain, constraints, like this is just an introduction. When I go, in more detailed analysis, okay, dynamic analysis, then I will be more specific, okay? But right now, this is the introduction, okay? So whenever a system is subjected to what? An external dynamic force, or even if there is no dynamic force, but there are, dynamic conditions inside, even without this, so that comes under dynamic analysis, okay? Now generally what happens? Now according to Newton's law, when you apply a force on a body, okay, this is a body, you will get a reaction, right? Newton's third law, for every action there is an equivalent opposite reaction, okay? Now in case of a dynamic situation, when you have a system applied to what? A dynamic loading, we also have some reactions. Okay, I mean, like, I am trying to explain these things in simple, very simple situation, okay, so that you will understand it and it will stick to your mind forever. Okay, now what happens, we have reactions, okay, as expected. Now we can possibly have three reactions, okay, in case of dynamic analysis. Okay, one reaction will be something which will try, because this force will try to displace it, right? It will try to maybe compress it, or maybe displace it. Okay, for example x. So there will be a reaction which will oppose this displacement, okay, and it will be equal to kx. Now this force, because it is changing with respect to time, it will try to induce what? Vibrations. Okay, it will try to, vibrations are what? When different bodies have different velocities. Okay, but initially this all of the body, when there is no vibration, all the particles, all the bodies have, sub bodies have same velocity. Okay, or the relative velocity is 0. But when you apply a dynamic force, there will be velocities, okay, increase in the velocity, okay, change in the velocity, and to resist the change in the velocity, there will be another reaction, we call it as cx dot. X dot is what? X is a displacement and dx by dt is velocity. Okay, so x dot means one time is differentiation, okay, that becomes d by dt. Okay, so dot means d by dt of x. Okay, x dot means d by dt of x, and that becomes velocity. Okay, now also because of this f of t, what is going to happen, the body, it is going to change the acceleration of the body. Okay, but there will be some reaction which will oppose the reaction, oppose the change in acceleration. Okay, and that will be the mass times acceleration, and acceleration is what? Acceleration is dv divided by dt, right? And v is dx by dt, right? So it is d square x by dt square, right? So m x double dot is the what? Acceleration. Okay, so when a system is subjected to what? A dynamic force, three reactions will arise. Okay, why reactions? Because they will they will oppose, they will, all of them, they will oppose it. Okay, oppose the effect. Okay, because f of t will change things here, and these reactions will try to this is because of the inertia, these will it will try to induce changes, right? But reactions will oppose. Okay, the reaction will oppose those changes. What are those changes? The external force is going to what? Maybe it will try to compress this body if this is fixed, or displace it. There will be one reaction, it is kx. Okay, but remember, in case of finite element analysis, because we divide a system into what? Discrete elements, right? Okay, right, we do the meshing, so this will won't be k, this will be k matrix. Okay, so the kx will oppose what? The displacement inside. The c is damping, by the way, this k is the stiffness. Okay, and c is the damping, and m is the mass matrix. Okay, now why k? Because what is k? K is stiffness is EI. When you induce a force, it will change the property and it will try to change E. Okay, so this is the reason K will oppose it. Okay, because the displacement, the deformation, okay, changes E and it changes K. Okay, of course it also changes I, and overall it changes K. That's why we have K here. Okay, then this f of t will what will increase, it will cause vibrations, right, in the body. It will change the velocities, and there will be this c x dot as a reaction, C is what? Damping. Okay, damping matrix. Okay, what it does basically, if V is the velocity, then what is the kinetic energy? Half mv square. Okay, so the kinetic energy will increase. Okay, then what is going to happen? The body will try to dissipate this kinetic energy. Okay, this f of t will cause this kinetic energy, right in this in the system, but system doesn't want, right, because system always opposes. So it will try to this is energy, right? It will try to dissipate this energy, okay, in the form of temperature or anything. Okay, so against this vibrations, because of vibrations there will be velocity, because of velocity there will be kinetic energy induced, and the Cx dot will dissipate this kinetic energy in different forms, like temperature, heat or something. Okay, and this C is damping matrix. Okay, also this external force will try to accelerate it, change the right, because first if it is static, it is uniform velocity, it will try to induce what? Acceleration, but the system doesn't want. Okay, so if it doesn't wants to accelerate, it will oppose f of t. How? With the help of mx double dot. Okay, so this equation we often use this in dynamics. Okay, mx double dot. Okay, so that is basically dynamic analysis. Okay, so let's move on. Then we have buckling. Now we know buckling is what? When you have a cylindrical body which one dimension is very large, okay, as compared to the other two dimensions, and when you apply an axial force, it will try to bend it laterally, right? So this is known as buckling. Okay, when you apply this force, also the axial, it will decrease. Okay, but this decrease, okay, let us call this as y, and let's call this x. Okay, x is very large than y. Okay, so in case of buckling, what happens? The bending stiffness, because it will bend like this, right? Bending stiffness is less than axial stiffness. Okay, what does it mean? It means, now stiffness is like property of the material, right? So when the stiffness is high, there is less bending. When the stiffness is low, there is low bending. Okay, because actually it didn't deflect much, it bent so much laterally. Okay, so the lateral stiffness, okay, or the bending stiffness is very much lower. Okay, so when you have such scenarios, that's called as buckling analysis. Okay, then we have other kind of analysis, thermal analysis, like when there is when you apply like heat to the body, the temperature, there is the temperature, the heat will travel from this point to this point, and the rate depends on what is the medium, what kind of heat transfer it is it convection, is it radiation, or what type. So those temperature related things, they come in the thermal. Fatigue analysis comes in when you apply the cyclic load. Okay, again and again and again you apply the load on a system. Okay, so that will ultimately cause the failure of the system, right? So that comes under the fatigue analysis. Then we have CFD. CFD is computational fluid dynamics. Okay, so the fluid mechanics things, the velocity and the boundary conditions of the fluid, okay, the shear stress, like etc. I mean related to the fluid. Okay, that is CFD. Then we have crash analysis. When you have like a car, for example, this is a wall. Okay, it is moving like this. Crash analysis, when it strikes the wall. Okay, this is a static body, or in other scenarios we have also one moving body suddenly what we call this as there are accidents and all those things. Then crash analysis talks about what is the safety of passengers inside, which component have more strength, what will be the stress distribution of the body, okay, what is going to happen to the passengers, and all those things that come in the crash analysis, and we can do that in FEM. Okay, then we have noise vibration. For example, you have an aeroplane, okay, you have this aeroplane. Now when you are sitting inside the aeroplane, you should there is not much noise, right? So the aeroplane is designed in such a way, when you stay inside, there is no much noise, okay. So but we have to see how much will be the noise from the engines and all those things. That kind of analysis is related to the NVH analysis, okay. So we can do all of these types of analysis in the finite element method, okay. And again, we will go to each topics in detail. This was just the introduction, okay. If you have any doubts, you can write in the comments, or you can contact me. And I think that's it for today. Thank you for watching, and see you in the next class.